A very good morning to all of you. For today's topic of electronic circuits, we are going to cover the semiconductors. Semiconductors are the material which have a conductivity between conductors and non-conductors. Conductors means metals and non-conductors means insulator like wood and conductors like metal like iron, etc. Semiconductors can be pure elements such as silicon or germanium or compounds such as gallium arsenide. So the pure form of silicon semiconductors we consider as silicon or germanium. Most of the example, these two semiconductors we are going to use. There are two types of semiconductors. One is known as intrinsic semiconductor and one is extrinsic semiconductor. Intrinsic semiconductor is known as pure form of semiconductor without any impurity. But in extrinsic semiconductors, it is known as impure form of uh, semiconductor. It has two types. One is N type extrinsic semiconductor. One is P type extrinsic semiconductor. We're gonna study all these semiconductors in detail. Your first type is intrinsic semiconductor. The pure form of semiconductors is known as intrinsic semiconductor. That is, there is no impurity, there is no extra electron or no extra hole in this semiconductor. This is known as pure form of semiconductor, which is known as intrinsic semiconductor. That is, holes and electrons are equal. Fermi level lies in between valence and conduction band. The Fermi level of forbidden gap is in between valence and conduction band. Ratio of majority and minority carrier is unity. As we said that holes and electrons are equal, so the ratio of majority and minority carriers is also equal. So the answer will be in unity. They have low electric conductivity and have low operating temperature. At 0 degree Kelvin, Fermi level exactly lies between conduction band and valence band. We already discussed this earlier in early point that when we talk about the Fermi level, in case of intrinsic semiconductor, the Fermi level should be lies between the conduction band and valence band. So the example for pure intrinsic semiconductors are silicon and germanium. Okay, now shifting to the example. Suppose this is the example of intrinsic semiconductor. We are considering silicon. So we know that the silicon atomic number is 14. So it has 4 electrons in its outermost shell. So we are showing here there are 4 electrons and all these 4 electrons making bond with other 4 electrons of silicon semiconductor. So there are balanced number of covalent bond. There is no free holes or no free electron in the circuit. So this is known as complete covalent bond. If this type of structure is given to you, that means it is an intrinsic semiconductor. Next is forbidden gap diagram, Fermi level diagram. So in case of intrinsic semiconductor, the Fermi level diagram should be like this. This is known as valence band. This is known as conduction band. And if the electrons of this conduction band needs to go to conduction band, the energy gap between them should be equal. Okay, and the Fermi level lies exactly in between conduction band and valence band. So this is the forbidden gap diagram of a intrinsic semiconductor. Next is known as extrinsic semiconductor. This is also known as impure semiconductor. An intrinsic semiconductor doped with a small and controlled amount of specific dopant, that is impurity atom, is called an extrinsic semiconductor. Means whenever we are considering the pure form of semiconductor, pure forms means intrinsic semiconductor. Dope means we are adding impurities. Okay? We are replacing one of its atom with some other impurity atom. Then it is known as intrinsic semiconductor. Okay. Here the charge carriers are produced due to impurity and may also be produced due to thermal aggregation. So the charge carriers which are going to be produced in here can be generated by two causes. One, due to impurities, we are directly adding the impurity. Second is by thermal aggregation, means by external heat or etc. They have high electric conductivity. The electric conductivity of extrinsic semiconductor is high, and also their operating temperature is also high. At 0 degree Kelvin, Fermi level exactly lies closer to the conduction band in N-type semiconductor and lies near valence band in P-type semiconductor. So there are two types of forbidden gap diagrams going to be formed. In case of first case, that is N-type semiconductor, the fermic level lies nearby conduction band, and in case of P-type semiconductor, the fermic level lies nearby your valence band. So example क्या होगी इसकी? When silicon and germanium dope with aluminium, arsenide, phosphorus, that is known as your extrinsic semiconductors. Why this? Because aluminium external aluminium atomic number is 13, so it has 3 electrons in its outermost shell, so there is always one vacancy in case of this aluminium. And when we are considering phosphorus, it has 15 atomic number, so it has 5 electrons in its outermost shell, so there is always one extra electron to form a covalent bond, due to which it form an yeah impurity. So these two examples of the example of N-type and P-type. Suppose here in case of silicon we are replacing it with the impurity that is known as phosphorus. Phosphorus atomic number is 15, so there are 5 electrons in the outermost shell, so 1 2 3 4, and this one is extra, that is 5. All 4 making covalent bond with the respective given silicons, but one will always remain free. So whole of the circuit will have extra charge, that is electron, that is negative charge. That why this is known as N-type semiconductor. Okay, it is also known as pentavalent impurity phosphorus, because pentavalent means it has 5 electrons in its outermost shell. This is also known as donor impurity. Why? Because there is one extra electron and it can denote one electron to some other compound or etc. Okay, but in case of boron, if we are considering the impurity boron, it has 3 electrons in its outermost shell. So only 3 electrons can make covalent with the respective silicons. One will always remain empty and it make an hole, a cavity that is known as hole. It has a positive charge, that's why it is known as p-type, and it can accept the electron, that's why it is called as acceptor impurity. So these are the two types of your n-type and p-type extrinsic semiconductor. If we're talking about the fermic level, n-type fermic level is like this. The fermic level lies nearby your conduction band. What is N-type extrinsic semiconductor? It is an extrinsic semiconductor which is obtained by doping the impurity, pentavalent impurity atoms such as phosphorus P, arsenic, etc. to pure germanium or silicon. Okay, the impurity atom added provide extra electron in the structure and are called donor atoms. The electrons are majority charge carriers here. In case of N-type extrinsic semiconductor, electrons are majority charge carriers and holes are minority charge carriers. And fermic level is near the conduction band. I already explained the example to you. Next is your P-type extrinsic semiconductor. In an extrinsic semiconductor which is obtained by doping trivalent impurity, as I told you, if in its outermost shell it has 3 electrons, that is known as trivalent impurity, such as boron, gallium, etc., to the pure germanium or silicon semiconductor. The impurity atom added create vacancy of electron, that is holes in the structure, and are called acceptor atom. Okay, the holes are majority charge carriers and electrons are minority charge carriers. In this case, the holes are majority charge carriers and electrons are minority charge carriers. Fermic level is near valence band. So this is a diagram for the p-type semiconductor when the fermic level lies nearby your valence band. I hope you easily understand the topic. Thank you very much.